we're going to talk about some drag force here. Now this is fun. Drag force is any resistive force that acts in the direction opposite of an object's motion relative to the medium that it's traveling in. The force that we've talked about that works like this is air resistance. There are other forces that will do this, but air resistance is the big one, or water resistance, or whatever, are the big ones that will act like this. This is complicated because drag forces involve forces that change with velocity. And of course, forces cause acceleration, and acceleration is a change in velocity. So as there's a force exerted, the velocity will change, which then causes a change in force if you've got a drag force that's related to velocity. So calculus needs to be involved. Now if we're going to do math with this, then we just rewrite Newton's second law according to the derivative definition of acceleration. Acceleration is the rate of change of velocity. So this is the differential form of Newton's second law, and that's what we're going to use to deal with drag forces. I'll write that up here as well. Sum of the forces equals m times dv by dt. All right. Now let me say to begin with here that some of what we do here you won't have the calculus for yet. And those are the things that I have put a star by. You notice right here, find an equation for its velocity as a function of time. You don't have the calculus for that yet. By the end of the year, you will. And so I'm going to, it's relevant to our curriculum now. I'm going to talk about it now. But like I said, you haven't done this calculus yet. But you should be pretty fluent in it by the time we get to the AP exam. So, this is a case where resistive force is proportional to velocity. And a good example of that is a small metal sphere falling through water or air or whatever. Oh, yeah. So resistive force is proportional to velocity. Cases where this is relevant, like I said, is small object falling through a liquid is a common example of this. Yeah. Or a liquid through... Sorry, my brain was freaking out for a moment there. So, this applies to objects falling slowly through liquids, and it also applies for very small objects. For example, a particle of dust in the air. That's when the magnitude of the resistive force is proportional to velocity. Now, if it's proportional to velocity and it opposes motion, the way we quantify that is we say it's negative, some kind of constant of proportionality. The book calls it b, so I'll call it b times the velocity vector. And I underline it to indicate that it's a vector. This resistive force is also a vector. And the negative tells you that that force is in the direction opposite of velocity. So if this object is falling through water, it's got this drag force. Okay, well, what else is acting on it? We've got gravitational force downward, and we've got the drag force going upward. So the sum of the forces is that drag force. Typically, it's easier if we call downward negative in these cases. So Newton's second law, it's just this, mg minus bv equals mass times dv dt. So we've got velocities in two different places. What is the sphere's terminal velocity? Now, I may have mentioned this. When an object is experiencing a resistive force, a drag force, because this drag force is proportional to velocity, eventually we reach a point where velocity is constant, because as this velocity gets bigger and bigger and bigger, then eventually the net force is going to be equal to 0. when this drag force winds up equal in magnitude to the gravitational force. And when that force is equal to 0, that means the acceleration will be 0, which means that the velocity will be constant. So when we ask what is the terminal velocity, that means we're looking for the velocity where the net force is equal to 0. And some simple algebra shows us that this terminal velocity, in the case of a drag force that is proportional to velocity, is just equal to mg over b. Now this, find an equation for its velocity as a function of time, this is something that you haven't done yet in your calculus class, but this is a technique that you will use later on in the year in calculus. When you have a differential equation like this, what you need to do is so everything here is a constant in time except for velocity. But you need to get the velocity on the same side of the equation as dv, and then take an integral to solve. So what you wind up doing is you multiply this dt over the other side. You divide this whole stuff to the other side because you need it on the same side as the dv. And then the mass this mass you can throw wherever you want. It's probably easier to stick it over here because mass is constant with relation to time and to velocity. And then to solve, we would integrate both of these, from 0 to t. So in this case, from v naught to v final. If we say that our initial velocity, if we say it's starting from rest, then this would be 0. But we just do the integral. 1 over m, this is linear in times. That's just 1 over m times time, evaluated from 0 to t, which would be 1 over m times time minus 0. So then we just have 1 over m times time. Okay. Hooray. And then on the other side of things, we have this function, which is something that you haven't dealt with yet. But if you have 1 over a linear, the integral of that is a natural log. So you don't really know that yet, but now I'm telling you. The integral of that is a natural log, and then via the chain rule, if you took the derivative of what's inside here, you'd get out a negative b, so to cancel that out, you need a negative 1 over b, which you would then evaluate from b final to b initial. And then once we're here, we plug in values and do some obnoxious algebra. So if we move this over, we've got a negative bt over m on the right side. On the left side, we plug in v final, which gives us natural log of mg minus b, v final. Plug in v naught minus natural log of mg minus b, v naught. Okay. Now, property of logs, if you're subtracting these two, then you can divide them inside one log. And then we want to solve for velocity, so we exponentiate both sides. And then we multiply this junk over. Subtract this, divide by negative b. And then if you work some shenanigans with where your signs are, and if you say that we're starting from rest, if we plug in 0 for v naught, then you get this slightly nicer looking expression. You eventually get out this slightly nicer looking expression. And this is the expression that you will find in your book. That's how it works. And at a certain point in the year, I'll expect you to be able to do this, but not now. The result is, it is what it is. I wanted to show you that now because it's something that will come up later on in the year. Now, another situation where we deal with the drag force. Sometimes drag forces are proportional to velocity squared. This is a key example of this is when you're skydiving. Generally speaking, a person-sized object falling through the air will experience a drag force that is proportional to velocity squared. So in this case, drag force is written as minus b squared. But that b for an object falling through the air is a specific quantity. The equation is this. Okay. And I want to just make sure we know this is not an equation you'll need to know for the AP exam or for my test or whatever. It's really just for the homework tonight, and just to give you some idea of where this is coming from. D is a dimensionless quantity. This is called the drag coefficient. And it's a dimensionless quantity. That depends on the surfaces in question. Rho is the density of air, or whatever the fluid is you're falling through, which is usually air. A is the cross-sectional area of the object. So in the case of a person skydiving, it would be the area of the front of their body or whatever, and V is the velocity of the object. So in this case, we've got an object. What forces are acting on it? It's falling through the air. Got gravitational force down, and we've got, I'm just going to write R, the resistive force going upward, which means that if we call up negative, down positive, Newton's second law, sum of the forces equals m by times dv dt. Well, we've got mg minus r, which is 1/2 d rho a v squared. And that's equal to m times dv by dt. This is something, again, on the AP exam, this is not an equation you can actually solve, a differential equation you can solve, but it is a differential equation that you might be asked to write on the AP exam. Just write exactly what I've written right here, something like this, and then you just leave it and not actually solve it. Terminal velocity, again, that's where the acceleration is 0, so that's where mg minus 1/2 d rho a v squared equals 0. So if we do algebra, then we find the terminal velocity is equal to mg multiplied by 2 divide d rho a square root. So that's the terminal velocity. Yeah. And this is Newton's second law. The differential equation you need to solve, you might just rearrange it, move the m to the other side, and divide this junk over to the right side of the equation. So that's how we deal with objects that have drag forces. This I will leave as an exercise for you. I can go over it when I return. Yeah, but it is solving this differential equation. It's essentially solving this differential equation in a case where there is no gravitational force, there's just this resistive force. So this is the only force acting, in which case this is just a polynomial. It's a v to the -2, which then you can use the power rule to integrate. So give that a shot, see how it goes, and then your homework is right here.